Hello. Yeah, I hope you guys are doing great. So this is my first video attempt that I'm doing. So here we will discuss about active filters tutorials. Okay, we have already covered the portions on how a filter behaves and all. So the derivation of a first order active filter was also dealt with in the class. So in this lecture we will be doing one tutorial based on the design of an active filter, and the simulation will be done in NI MULTISIM. So we'll just go straight to the question. So this is the question that I have giving. Design a first order low pass filter for a pass band gain of 4 and for a cutoff frequency of 4 kilohertz. So it means that the filter should pass all the frequencies below 4 kilohertz. Correct. Now obtain the frequency response and hence plot the magnitude and phase spectrum of the designed filter. Use SME log sheet. What will be the output of the filter if the input is first case 2 sine 200 pi t, and the second case the input is 2 sine 200,000 pi t. So to plot the frequency response, that is the magnitude spectrum and the phase spectrum, I'm giving a set of frequencies, that is 10 Hz, 100 Hz, 1 kHz, 2 kHz, 3 kHz, 4 kHz, 5 kHz, 7 kHz, 8 kHz, 10 kHz and 100 kHz. So I hope the question is clear. So we have already drawn the circuit diagram of a first order low pass filter. This we have already covered in the class. So you can see the capacitor. This is the capacitor is grounded. So this is the RC network that actually will be doing the filtering. Now RF and R1 constitutes the gain. So this is used in a non-inverting configuration. Now the passband gain we have derived in class that it is given by AF is equal to 1 plus RF by R1. So in the question we need a passband gain of 4. So what will happen? AF is equal to 1 plus RF by R1 should be equal to 4, which means RF by R1 equal to 3, which gives you RF is equal to 3 times R1. Now let us take R1 as 10 kilo. You can take whatever you want. So I would suggest you take more than 1 kilo ohm. So here I am taking 10 kilo ohm. So if R1 is 10 kilo ohm, RF will be 3 times 10 kilo ohm, which is 30 kilo ohm. Now the higher cutoff frequency FH of a first order low pass filter is given by FH is equal to 1 by 2 pi RC. So in the question the cutoff frequency is given as 4 kilohertz. So 1 by 2 pi RC should be equal to 4 into 10 power 3. Now let us take for the design C is equal to 0.01 mu f. Again it depends on what capacitors you have. I would suggest you to take 0.1, 0.01 like that. So 0.01 mu f I have taken. Then R can be calculated using the cutoff frequency formula. So R you will get as 1 by 2 pi FHC. You will get it as 3978.873 ohms, which is equal to 3.978 kilo ohm. So now we can plug in the values into the circuit diagram. So here you can see R1 we have taken 10 kilo ohm, RF is 30 kilo ohm, which will give a pass band gain of 1 plus 30 by 10, which is 4. Now R is 3.978 kilo ohm and C is 0.01 mu f. Now let us proceed to plot the magnitude and phase response, or this phase magnitude and phase spectrum. The frequency response of a first order low pass filter is given by G. The gain is equal to HF is equal to AF by 1 plus JF by FH. This also we had derived in the class. So here we will be using this AF divided by 1 plus JF by FH. So the magnitude response will be absolute value of this, correct? So absolute value of AF divided by 1 plus JF by FH. So absolute value of AF is AF, and absolute value of the complex quantity 1 plus JF by FH will be square root of real part square plus imaginary part square. So here the real part is 1 and the imaginary part is F by FH. So the magnitude will be 1 plus square root of 1 plus F by FH square. So finally you will get AF is 4. So 4 by square root of 1 plus F by FH is 4000. So F by 4000 square. So this is the magnitude response. So now if you plug in the frequencies here, you will get the response. You can start from 0 Hertz to very high frequency and you will get the response. Now next we'll find how to plot the phase response. So phase of a complex quantity is quantity A plus JB is tan inverse imaginary part by real parts. So A plus JB, it will be B by A. Correct. So here what happens is that you have a complex numerator is AF. So AF is AF plus J0. So the phase of AF plus J0 is tan inverse 0 by AF, which will be 0. Denominator, it will be tan inverse F by FH by 1. So you will be getting 0 minus tan inverse F by FH, which is minus tan inverse F by FH. So it is minus tan inverse F by F 4000 because FH is equal to 4000. Now we can find the magnitude and phase at the frequency points given. So the frequency points given were 10, 100, 1000, 2000. Correct here. So now let us, as an example, I will show how we are calculating for a particular frequency. So gain at 10 Hertz will be 4 by square root of 1 plus 10 by 4000, which will be equal to 3.999, which is 4. So gain in dB will be 20 times log of gain, which is 12.04 dB. Now phase will be minus tan inverse F by 4000, which is 10 by 4000, so it is minus 0.143 degree. So similarly we will calculate for all the frequencies like 10, 100, 1k, 2k. You just have to substitute these frequencies and you can formulate a tabular column like this. So this is the gain and this is the gain in dB and this is the angle in degree. So now let us plot the magnitude spectrum. So we'll be taking a semi-log sheet. You know that semi-log sheet means the x-axis will have the logarithmic. So first I am taking 10. F frequency is 10, 100, 1000, 10,000 and 100,000. Clear? So this was the range that was given. So at 10, what was the gain in dB? 12.04. At 100 it was 12.04. At 1000 whatever value, like that I have marked the values in circles, all the gain values. Now you just have to join those points and you will get the magnitude spectrum. So you can see that it is a low pass filter, correct? Low pass filter, which will pass the low frequencies and it will stop the high frequencies. Now similarly for the phase, we will mark the points. At each frequency we will find the phase and it is marked. So frequency and phase is marked. Now to plot, now we join it using smooth curve. This is not that smooth because I drew straight lines here. So if you, while drawing, you just use smooth lines so that something like that you will be getting. Clear? So this is the phase response. So now another question in that was output of the filter when the input is, first case it was 2 sine 200 pi t. So normally an input is represented as Vm sine 2 pi ft. Correct. So here 2 pi f is 200 pi, which means frequency is 100 Hertz. So 2 pi f is 200 pi, which means f should be 100 Hertz. So for this signal, the frequency is 100 Hertz. Now from the table, we have already found out what is the gain and phase at 100 Hertz. Correct. So gain at 100 Hertz is 4 and the phase is minus 1.9, 1.43. So that is what we have written here. Okay, the gain of the filter at 100 Hertz is 4 and gain is minus and phase is minus 1.43. So output will be what? 2 into the gain, that is 4, into sine 200 pi t. So an additional phase of minus 1.43 will be coming. So minus 1.43 degrees. So 8 sine 200 pi t minus 1.43 degrees is the output when the input is 2 sine 200 pi t, which means that you are getting that signal actually, correct? Output is actually amplified 8 times you are getting, sorry, 4 times you are getting the output, and it is there, the signal is present. Whereas now in the second case the input is 2 sine 200,000 pi t. So 2 pi f will be equal to 200,000 pi, which means input frequency will be equal to 100 kilohertz. Okay, so from the table we know that the 100 kilohertz we have calculated the gain and phase. So gain of the filter at 100 kilohertz is 0.16 and the phase is minus 87.71. Here you can see 100 kilohertz 0.16 is the gain and the angle is minus 87.71. So that we are substituting here. So what will happen? 2 into 0.16 into sine 200,000 pi t minus 87.71. So this will be the output. You can see that the output amplitude is drastically reduced. Earlier the amplitude was 2, now the amplitude is only 0.32, which means that this high frequency is actually stopped by the filter. Clear? So this is the tutorial first part, that is the design of a active low pass first order filter. Now let us see what happens in the simulation. So I have already wired the circuit here. So this is the circuit using multisim. We have wired the circuit. So R1 is 10 kilo ohm, RF is 30 kilo ohm, R is 3.978 kilo ohm, and C is 0.01 mu F. I am giving plus 15 and minus 15 as the supply, and the input voltage I am giving V in 1 volt peak. Okay, 1 volt peak and 1000 kilowatts. But here I am interested in the frequency response characteristics. So in the right panel you can see something called as the Bode plotter. Here you can see this. So this I will take. Okay, so Bode plotter, it has two terminals. One is the input terminal and the other is the output port. Okay, so input we will connect to the input and output will be connected to the output of the op-amp. Now ground also we will give. So I will take a ground. Okay, and this is the ground. I am connecting the negative of the input and the negative of the output to the ground. So this is over. Now run it. Double click on this Bode plotter. You will be getting the Bode plot. So frequency, so this is the maximum of the frequency. I don't want to see up to 1 gigahertz. I just want 100 kilohertz. So I will just reduce this to maybe 100 kilohertz. Clear? And 1 millihertz is the minimum, so I will give it 1 hertz. Okay, so 100, 500 millihertz, 1 hertz. To see this properly, I will increase this thing so that we know that it is something around 12. So I'm giving maximum as 20 and minimum maybe I will give like this. So you can see the frequency response. This is the magnitude spectrum. Clear? So you can see that this is the cursor, you can move it. So here the frequency, the gain is 12.04, which in using our formula we had actually got 12.04, correct? Now the cutoff frequency can be found by reducing this 12 by a factor of 3. So 12 minus 3, how much is that? 9, correct? So we will go to a point where it is 9, or you can right click here, set x value I'll give as 4000 because we designed it for 4000, correct? So here you see at 4 kilohertz the value is 9. At maximum gain was what, 12 dB, so 12 minus 3, 9 dB. So this is the cutoff frequency and this is the bandwidth. Okay, so up to 4 kilohertz the signal is actually passed, whereas any signal after 4 kilohertz the gain will be drastically reducing. Clear? Here one more thing you can see if you want, at this point let us take the case when the it is 10 kilohertz. At 10 kilohertz what is the value? 3.4 dB, correct? Now go to 100 kilohertz, 60.5. So you can see that there is a 20 dB drop when the frequency was multiplied by 10. The gain reduced by 20 dB. This is why I told you in the class first order filter will have a slope of minus 20 dB per decade. So frequency here is 10 kilohertz, this is 100 kilohertz. Here what was the value? Around at 10 kilohertz the value was around 3.4. Here it is around 16, which means the minus 16, which means the gain has reduced by 20 dB almost. So you can see that the slope is 20 dB per decade. Now phase also you can see. So phase is this. So don't give this much. So we know that it is somewhere around 0 and minus 90 only. Correct. So you can see this is the phase. Can you see this? So this is what we've got also actually. Correct. So one and maybe this I will just reduce even further so that we can see it properly. Okay. So that is it. The simulation, the magnitude as well as the phase spectrum is plotted. I hope you understood. We'll continue with the next video wherein I will be designing a high pass filter. Thank you.